everyone. Myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to deliver you the lecture on solution of wave equation in cylindrical coordinates. So, solution of wave equation. As we have done for the rectangular waveguide in our previous lectures, the circular waveguide also uses only a sinusoidal steady state or frequency domain solution will be attempted. Now, before starting this, what we have to do? We have the scalar Helmholtz equation in cylindrical coordinate, which is given by this expression. Now, so solve this equation. Since we have to solve this equation, we have to get the solution of this equation in this lecture. So, we have to use the method of separation of variables for finding out the solution. So, for that we are assuming that the psi. So, what is the value which we have to calculate here? That is the psi here. And these are the, we know that for the cylindrical coordinates the values are r, phi and j. So, differentiation in the terms of this one, and gamma already known to us, which we have encountered this term already in our rectangular waveguide expression, that is our propagation constant. Now, so we have assumed that psi should be equal to r phi z. R is a function of the r coordinate, phi coordinate and z the z coordinate. So, what the first thing we do for solving this? Substitute this solution in the Helmholtz equation, already we have. So, what we will do? We will substitute 1 by r, let me first erase the, let do 1 by r del upon del r, and the place of phi, we will psi, we will write r, phi and z. R, phi, z, I am not writing the function here for the simplicity, plus 1 by r square del square r phi z del phi square plus del square r phi z upon del z square r phi z. So, what we are doing now? We have, when we solve it, this will be 1 by r. Since here we can say that phi and z is not a function of r. So, it can be treated as a constant here. So, phi and z outside, del by del r plus 1 by r square. Similarly, r and z is a constant here. And in this, when we are differentiating in the terms of z, r and phi are the constant. So, we are taking this outside, del square z by del z square gamma square r phi z. So, this is the first thing which you are doing. So, what is said here? So, solution of this substitution of this solution in a Helmholtz equation, we have done with this. Then the next expression is what we have to do? Division of the resultant by the solution again. That means we have to divide this resultant with the solution, which is equal to r phi z again. And when we divide it with the help of r phi and z, phi z cancel, we have denominator r. So, if you are able to see 1 by r, we are getting this one. Now, in this r phi z division, r and z cancel, we have phi. See. So, similarly, r phi z, r and phi cancel, 1 by z. So, we are having this expression, and when we divide this one, completely cancel, and we are having gamma square. So, now we are have this equation. Now, if we are able to see that all these are the independent equations. So, since the sum of the three independent terms is constant, gamma square is a propagation constant, it is simply a constant. So, we can assume that each of the independent term is constant here. So, we are assuming that the z direction our wave is propagating inside a waveguide, inside our circular waveguide. So, the third term may be set equal to propagation constant in a guide expression. So, del square z is equal to dz square upon gamma. So, if we are assuming that our third term is equal to gamma g square, so what will be this give? 1 by z d square z upon del z dz square should be equal to gamma g square. So, this z this side, so d square z upon dz square is equal to gamma g square z. This is the expression, and we know the solution of this are given by this one. Okay. Z is equal to a e to the power minus gamma g z b e to the power gamma z z, where gamma g already told to you propagation of constant of the wave in the guide. Now, we insert this gamma g for the third term in the this expression. So, what we are getting? What we have to do? 1 by r r d upon dr r dr upon dr plus 1 by r square phi d square phi upon d phi square, and here we are doing gamma g square is equal to gamma square. So, and now, so we are getting this expression, and now what we are doing? After inserting this gamma g square at the place of this one for third term, we are multiplying the resultant by the r square. The complete resultant which we are getting, we are multiplying that with the r square. So, when we multiplied with the r square, here are this r square get cancelled, and we have 1 r by r d upon dr r dr upon dr plus 1 by phi d square phi d phi square plus gamma g minus gamma square r square should be equal to 0. This is the expression which we are getting. Since we have it is taken gamma square first, that is the minus here, and when we expand it, this will be the gamma g plus square. So, now the second term, this second term is a function of phi only, hence equating the second term to a constant that is equal to minus n square gives what? With this we will give this expression, d square phi d phi square minus n square phi, and the solution of this is a harmonic function. So, the solution of this will be in the terms of harmonic, and we will have phi is equal to a to the power a to the subscript n sin n phi plus b subscript n cos n phi. Now, when we are replacing this minus n square in our this expression, what we are having at the place of d square phi d phi square, what we have to do? We have to substitute that with the minus n square phi. So, go through that. Plus 1 by phi, and at the place of d square d phi square, we have to substitute minus n square phi. This phi get cancelled, minus gamma square minus gamma g square r square is equal to 0. This is the expression which we are getting. And now, the second thing is here that which we have done, that at the place of Kc square is equal to minus gamma square minus gamma g square. So, what the next thing we can do, that at the place of gamma square minus gamma g, we can have the minus Kc square r square is equal to 0, and that expression is written here. Okay. And what we have done next, we have multiplied throughout what we have achieved now by replacing the minus gamma square minus gamma g square by Kc square. What we have achieved, we are multiplying that with r and we are able to get this expression of our expression. Now, this is the characteristic equation of the Bessel function. So, what we have achieved now is the characteristic equation of the Bessel function, and for the lossless guide, this characteristic equation reduces to beta g is equal to omega square mu epsilon minus Kc square. So, the solution of the Bessel functions are, Bessel equation is r is equal to C n Zn Kcr plus Dn Nn Kcr, where Zn Jn Kcr is the nth order Bessel function of the first kind. What is representing? It is representing standing wave of cos Kc square for r less than a. So, what we have calculating here, in this condition a is the basically our circular waveguide radius. So, the main parameter which is existing inside a circular waveguide is basically the radius which is having, and the radius is equivalent to a. So, if this is the nth order Bessel function for the first kind representing standing wave already known to you, when the incident and the reflected wave both combine, we get the standing wave, and this is only achieved by us when there is a mismatch in the transmitting and the receiving end. So, standing wave of cos Kc square for r less than a, and Nn Kcr is the nth order Bessel function of the second kind, and what is it is representing? It is representing standing wave of sin Kcr for r greater than a. And when we see the expression of this first kind and the second kind, since the first kind is the cos Kcr, standing wave of the form cos Kcr, so it will be having a maximum value of 1 at 0 and it will changes. Now, Bessel function of the second kind sine, it will not get a value on the 0 side, and then you will have this. So, students, till now we have achieved what? We have achieved the solution of the Helmholtz equation finally, but for the recap of you, why I once again tried to go through the steps which we have done here. So, what we have done? First, we have a Helmholtz equation in the cylindrical coordinate system. We in the cylindrical coordinate system r phi n z. So, we have this expression of the Helmholtz equation, which is our wave equation in the terms of cylindrical coordinates. And now, the first thing which we are doing to, we have to find the solution method by the method of separation of variables. So, method of separation of variables, what we do? We assume that what will be the solution of the expression, and here we are assuming that the solution which is required to us, that is psi, should be equal to r phi n z. So, we have assumed that psi equal to r phi n z. Now, what the first thing we have done? We are going to replace this psi with r phi n z. So, when we replace this, what we are having? And now, what the expression whatever expression we will get after the replacing, we divide that complete expression again with the r phi n z, that which is our solution. And what we are getting? We are getting this expression. So, all of you are requested to kindly solve it parallelly, so that you are able to get it. Now, the next thing which we are having, that since we are assuming here that the gamma square which is obtained here is our propagation constant, So, each independent variable sum should be equal to constant. So, we can have this, we can solve this independently. So, in that case first what we have to do, the third term which is equal to what? The third term is this one. So, we are assuming that it should be substituted with gamma g square. So, if we substitute this expression with the gamma g square, what we are getting finally? This one, d square z upon dz square is equal to gamma g square z, and the excuse me, the solution of this equation are given by this one. So, we are able to get the solution which is required. This expression is with us. Now, we have to find out this two, and by multiplying we are able to get the complete solution of the psi. Now, we have obtained the value of the d square z by dz square. So, we substitute this expression in the already existing expression. So, we are able to substitute this, and what we are getting now then, and multiplying the resultant by r square, and whatever resultant which we get after substituting the gamma g square there, we multiplied that with the r square, and we are able to get this expression. Now, we have already solved the expression for z. Now, we have to solve it for the phi and r. So, now we are moving towards the phi. So, the second term is a function of phi only, hence equating the second term to a constant minus n square give what? D square phi, d phi square is equal to minus n square phi, and if you are able to see this, this is a harmonic function, and in so phi should be equal to a n sin n phi plus b n cos n phi. Replacing the term phi by n square in the equation, this equation exactly, and multiplying that with a capital R. We are on the second thing which we have to do is that we have replaced the gamma square minus gamma g square with a kc square, and by doing this we are able to get this expression. So, what the step by step, if you go to the step by step, what the first thing which we have to, we write the equation in the cylindrical form, then what we have to do, that we have first use the method of separation of variables r, phi and z, and then substitute the value of psi equal to r, phi and z. Whatever expression we get, we multiplied with the r, phi and z, and then the first important expression is achieved by us, where on the right hand side we see that there exists a simple constant, that is the gamma square. Now, if the summation of three independent terms is the gamma square, so we can solve it independently one by one and assume that it should be equal to constant. So, first on the z function, we are assuming that the wave is propagating in the z direction inside a waveguide. So, we replace that terms with a, solve that terms with the help of a propagation constant of a waveguide, that is equal to gamma g. And when we, the next thing, phi is a harmonic function. So, we obtain this, and now our approach is to find the r. For that, whatever expression we would get after substituting gamma g and phi, we will multiply throughout by r square, and gamma square minus gamma g should be equal to kc square. We will get the characteristic equation, and this equation is in the form of Bessel function. So, we are getting the Bessel functions here, and now we have the value of r, phi and z. So, when we multiplied this 3 r, phi and z values one by one, we are able to get the expression which is required by us. Now, the second step is to find this is the total solution, but we have to minimize this expression. So, for that, first of all we write the boundary condition, and when we apply the boundary condition, this expression reduces to 0, and this can be shortened in the form of magnitude and the phase. This form we will be able to get this, and so this is Cn, Zn, Kcr, Fn cos n phi e to the power plus minus j beta gj. All the constant Cn and Fn phi naught. Bessel functions cos n phi e to the power minus plus minus j beta. So, this is the final expression for the solution of the Helmholtz equation. So, keep on studying, and thank you for attending today's lecture.